So in the next part of class here, we're going to start talking about electricity. And the first part of this, we're going to talk about what they call electrostatics. That's static electricity, right? We're going to talk about charge, we're going to talk about electric fields, we're going to talk about electric potential, and then later on, we're going to talk about electric current and circuits. And the first part of this here that we're going to talk about is about charge. And our target is to be able to predict the force between charged particles. So let's go ahead and let's get to that. Okay, some important stuff to note that some of it you're probably already aware, but we should talk about it as we start talking about electricity here. Today we're talking about charges. And charge is a property of a thing that's kind of hard to define, but you kind of already have some intuitive understanding of charges. You've taken chemistry with me, probably, and we talked an awful lot about charges of things like ions and electrons and protons and stuff like that. So charge is not like an entirely new concept, but some things that we need to mention and some things that we need to have in our heads, right? First, there's more than one kind of charge, right? There are two kinds of charges. We tend to call them positive charges and negative charges. That doesn't necessarily mean that one of them is more than zero and the other one is less than zero. It's really more like there's two different kinds. And interesting figure actually named them positive and negative, somebody whom you might remember from his small role he played in history class, and that would be Benjamin Franklin. Right, Benjamin Franklin. You've probably heard the story of the kite with the key on it, and he went out in the thunderstorm and flew his kite with a key on it, and there was electricity or something. I don't know how true that was. I wouldn't go flying a kite with a key on it out in a thunderstorm, you know. Apparently he survived to play some role in the founding of our country. Also invented the lightning rod, as I understand. So, interesting character there. But Benjamin Franklin named our two kinds of charges positive and negative. Makes sense. There's two different kinds. Let's call them positive and negative. Some things that we need to understand about those positive and negative charges. Charges that are the same type, either both positive or both negative, those charges will repel each other. They'll move away from each other. They'll experience a force that pushes them apart. Charges that are different types, that is one positive and one negative, will attract each other. They'll move together. They'll experience a force that pulls them together, right? So opposite charges attract each other, and like charges repel each other. Something we need to keep in mind there. A couple more important things to note as we're talking about charge here. Charge is measured in a unit called the Coulomb. It's named after this gentleman here, who was a French scientist by the name of Charles Augustin de Coulomb. And so the unit for charge is called the Coulomb, after him. Coulomb is a capital C we use. So 3 with a capital C means 3 coulombs of charge. Can be positive or negative, obviously, right? Because we have positive charges and negative charges. And when we want to use charge in an equation, the variable that we use for charge is a Q. Sometimes people use a capital Q, sometimes people use a lowercase. Either one is acceptable. So a Q, either uppercase or lowercase, stands for charge. So in this scene, I tried to talk about what causes an object to become charged. And as I recorded this scene, I learned that my electrostatic generator does something to my microphone such that you can't hear me very well. So I've re-recorded the scene, and I've recorded the audio separately so that you might be able to hear me as I talk. Now, there are some objects that just naturally have a charge. Protons, electrons, they just naturally have a charge, right? But how do other things, like things in our everyday lives, like this electrostatic generator, or some other objects, how do they acquire a charge? Well, there's two different ways that things can become charged that we're going to talk about here. One way is called charging by induction. And as you see me in the video, I'm taking some little bits of paper and I am dropping them near the electrostatic generator. And what you can probably notice is that at first they move straight towards the generator, And then once they touch the generator, they start moving away from the generator. So, they move towards and then they move away. So pretty interesting there. What happens there is that, as the generator is on, it generates a charge in the sphere, a large charge. And so what happens is that large charge will either push or pull on the electrons that are in the paper. And then the electrons in the paper end up going towards one side of the paper or the other side of the paper. And then one side of the paper has a different charge than the electrostatic generator, and it's attracted towards the generator. Now, once it touches the generator, a different kind of charging happens. This one is called charging by contact. Let's assume for a minute that the generator has a negative charge. So it has extra negative charges. So when the paper touches it, some of those extra negative charges will move on to the paper. And now the paper will be negatively charged, and the generator will be negatively charged. They'll both have different charges. And so they'll experience a force that will move them apart, a repulsive force. And this is when you see the paper shoot off into the air off the generator. You can also notice this with the strings that are on the top of the generator. The strings on the top, they're touching the generator, so they will take on the same charge that the generator has. Right? So if the generator has a negative charge, the strings will also take on a negative charge. And because they have the same charge, the generator and the strings will repel each other. And because all the strings have the same charge, each string will repel each other string. So you'll see them stand straight up on end. Pretty neat, huh? Let's take a closer look at charging by induction here. This is kind of an interesting process, right? You can see over here I have an object with a big negative charge. Doesn't really matter, it's got a big negative charge, let's say. And over here I have just some other object. You can see there are just as many pluses as minuses in it. So the positive charges and the negative charges can cancel each other out. So this would be electrically neutral. It would not have a charge. However, bringing this object close to the one that has a large charge, what's going to happen is these negative charges are going to repel these negative charges, right? And so what's going to happen is it's going to push them over towards this side of the object. Now the positive charges in objects don't move so easily, so we're going to say they just kind of stay there. If these weren't actual particles, then we could say the positive charges would move towards that side. But in an actual object, they don't move so easily. Okay, now you can kind of look at it and you can think about it for a minute and check it out. If we were to draw kind of a line straight down the middle, on this side of the object, there's really only positive charges. So this side of the object becomes positively charged. This side of the object has many more negative charges than positive charges. So this side of the object is negatively charged. So what's going to happen? This side is positive and that object is negative. Since they're opposite, there's going to be a force pulling it this way. And this is what charging by induction is. It's not really changing how much charge is in the object, it's just changing where it is so that parts of it have different charges. Okay, we can kind of use the same picture to talk about charging by contact. Let's say, this guy is getting pulled towards this one, and let's say they actually come in contact with each other. What's going to happen? Let me move this one. It'll be easier to redraw. Okay, so we have our object with many negative charges coming into contact with our object that has just as many positives or negatives. Okay. Well, charge likes to kind of even itself out. So once they come into contact, many of these negative charges will move over onto the other object to even things out. And until both objects have the same amount of charge, right? And so this is what's called charging by contact. So when this is charged by contact, it actually does pick up more charges than it had before. Or if the situation was reversed, if these were positives, it can lose charges that it had. Whereas with charging by induction, it doesn't actually change how many charges, it just kind of separates them, right? So charging by induction and charging by contact. If we want, we can mathematically predict the force between two charged particles using what's called Coulombs Law. Here's Coulombs Law. It says F equals Kc Q1 Q2 over R squared. Now F is the force between the charged particles. Force is measured in newtons, you remember. Q1 and Q2 are the two charges. So this is the force between two charged particles. These are the charges of those two particles, Q1 and Q2. R is the distance between those charges. When the charges move closer together, there'll be more force between them. If they're further apart, there'll be less force between them. And then you can see Kc here is what's called Coulomb's constant. Kc, it's just a number, and it's equal to 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Right? And it's just always this number, 8.99 times 10 to the 9th power. Okay, when you're using Coulomb's law here, some important things to note is that a negative force, if you have a force that is negative, you get a force that is attractive. So, think about that Q1 and Q2. If one of those is positive and the other one is negative, then your force is going to end up being negative, which means that you have an attractive force because the opposite charges attract. If you end up with a positive force is repulsive, right? So, let's say Q1 and Q2 are both positive. A positive times a positive is a positive. Or if they're both negative, a negative times a negative is a positive. So either way, your force comes out positive, and two charges that are the same should be repulsive, right? So a positive force is repulsive. Let's talk about a couple of situational what ifs with this, right? Maybe we don't actually put some numbers in the equation and work it out. Maybe we're just kind of looking for what would happen in general. What would happen if we doubled one of the charges? What would happen to the force? So if I doubled this charge or I doubled this charge, one or the other, what would happen to the force? Well, then we would have, this would be twice as much, then this would be twice as much. The whole thing would be twice as much. So if I double one of the charges, I'm going to double the force. What would happen if I doubled both of the charges? If I doubled both of the charges, this would be twice as much, and this would be twice as much. 2 times 2 would be 4, so this whole thing would be 4 times as much. So if you double one charge, you double the force. If you double both charges, the force is 4 times as much. What'll happen if I change the distance between the two charges? What would happen if what would happen to the force if we doubled the distance? Okay, well, you'll notice the distance is squared. So if we doubled it, think about, doubled is 2. So if what is 2 squared is 4, right? And it's in the denominator, it's in the bottom. So instead of 4, let's think about 1/4. So if I double the distance, then the force will be 1/4 as much. What if I triple the distance between them? What would happen? Okay, well, triple 3 squared is 9, so it would be 1/9 as much. So tripling the distance makes the force 1/9 as much. What if I make the distance half as much? Well, a half squared is 1/4, and then it's in the denominator, so 1 over 1/4 is 4. So if I half the distance, the force will be 4 times as much. So we can kind of look at the layout of the equation and determine kind of what's going to happen if we make some changes to those charges and distances. So there is a little bit about charges. Charges, Q, capital Q or lowercase q, either way. Charge is measured in coulombs, which is a capital C. There's a little bit about charges there. Hopefully that helps us to be able to predict the force between two charged particles. So until next time, take it easy.